Hello, welcome to this virtual presentation for ARM Summit 2022 on dynamic routing of machine learning workloads with CNCF wasmCloud. I'm Steve Shetler. I'm a serial entrepreneur. I work on high-scale distributed systems, machine learning, and security. I'm a co-founder of Zynga that brought you Words with Friends and Farmville. I'm a co-founder of Cosmonic, where I work on product development and customer success. Cosmonic is the creator and maintainer of the open source wasmCloud. Today we're going to talk about the challenges in developing machine learning applications and the importance of finding the right level of abstraction and what can go wrong if we don't have the right level of abstraction. We're going to talk about what is wasmCloud and what about wasmCloud lets us add amazing features in our apps like policy-based dynamic routing. What kind of apps are we talking about? The kind that are everywhere. They're on the device in your pocket, on the utility pole, in your car. Even though the environments where these apps run are pretty diverse, the challenges that we use to develop these are pretty similar. Developers have to move from inception to production. And the environment is also dynamic. Networks go up and down. When you pull the car into the driveway, you might have access to the house Wi-Fi where you get higher speed internet. Or you might be driving after a storm and the power lines were knocked out and your app has to figure out how to route around the failure and provide partial functionality even in the absence of intermittent network. To address these challenges, we start back at the design phase while we're gathering requirements. And of course, when we're creating a new product, the first thing we start with is the features. What is it going to do? But in addition to the features, it also has to scale. It has to be secure. It has to be reliable. We call these other kinds of requirements non-functional requirements, or NFRs. They're just as important as the features because we can't ship an app without it. In addition to thinking about what we're building, there's how it's going to be built. Developers have to create pipelines, have to be able to move software from a development workstation to staging to production. Hopefully we can do it without having to learn a new suite of tools every time we change environments. And gosh darn it, development should be fun. Shouldn't have to worry about overhead and inefficiencies in our development process. Unfortunately, where a lot of the time goes in development is these non-functional requirements. An internal Capital One study found that over 80% of developer time is spent building non-functional requirements. And over 90% of the total cost to create an application or a service, and over 90% of the lines of code are not creating new features for our end users. They're supporting non-functional codes. They're replicating boilerplate and templates just to get an app working. So how do we as developers get beyond that? What kinds of abstractions can we use to be more productive in development so we can build more features, better features for our users? One of the most significant changes has been containers. Early on in 1979, Bill Joy added chroot jails to the Unix kernel, which provided a file system isolation. About 20 years later, VMware introduced VMware Workstation, which gave another level of abstraction where we could run multiple OSs on the same system. Soon after that, Zen Project launched with their hypervisor. There was a period of lots of hypervisors and paravirtualization. This was at the time when the internet was just beginning to take off. And those technologies enabled cloud providers like Amazon AWS to create hosting for multi-tenant applications. Then around 2013, Docker launched their first version of containers. And soon after that, a group at Google said, we need a way to orchestrate these Docker containers let's create Kubernetes, another open source project that was based on an internal project from Google called Borg. What were we trying to accomplish with these containers in Kubernetes? We wanted to get scale. We want to take an app and replicate it out to handle our large traffic. We want to do orchestration, and we want to abstract away some of the underlying things that go into building every app. And one of the things Kubernetes is known for is being not too hard for building an app the first time and getting something running. But if something breaks, it's notorious for being hard to debug because the layers of abstraction dissolve away, and you're forced to have to become an expert in the underlying technologies to be able to debug and diagnose it. That's a term called leaky abstractions that Joel Spolsky wrote about in 2002, where he said, paradoxically, even though we develop higher and higher levels of abstraction, it's becoming harder and harder to become a proficient programmer because of all the extra complexity we have. Now, I'd ask, if you're using Kubernetes, has it made it easier for you to address the non-functional requirements? Does it make your security simpler? Is it easier to choose a database vendor or the protocol you're going to use to talk between the backend services? If not, then we've created other kinds of constraints. Over a 40-year period, we went from a cheroot jail to a container jail. Let's dive in a little bit to the container. At the boundaries of a container, we have a TCP/IP interface, a socket interface, file system namespaces. And because they're low level, they're pretty versatile. But it means if you want to do anything higher level in your app, you have to put all those other layers of abstraction into the container. If you're using a microservice API, say REST, to communicate between containers, there's a pretty good chance that your app is also using JSON for serialization. And there's also a pretty good chance that there's some exposure in your code to the HTTP status codes. What is a 404 or 302? You might be doing long polling. You might build in retry loops because you're not sure if the network is reliable from the client to the server. And you're probably using DNS to locate and find the other containers and services on the network. So all we wanted to do was send a message to another app, to another object, issue a query. But instead, we have all these other layers that we have to understand and manage to be able to accomplish just calling a function remotely. Another thing we wanted to get was simpler packaging. But what we got was tight coupling to services. You had to decide early on in development what database driver you're going to use or what logging library you're going to use, because those libraries had to be bundled into the container. That creates an exposure of supply chain vulnerabilities, like the Log4j vulnerability. And it's not just the fact that Log4j had a vulnerability. Those happen. When they happen, we want to get them out of our system as quickly as possible. Log4j was in the news and a major event worldwide because millions of containers had to be rebuilt because they all had the same library in them with the same vulnerability. In addition, because we're compiling so much into our containers, we're replicating a lot of code. It means we can't put as many in a virtual machine, and we're not getting as much efficiency. We're increasing our carbon footprint. And we also hope to get portability. Containers were supposed to isolate us from the operating system. That is still basically Unix. And if you tried to reduce the size of your container, you probably looked into Alpine Linux. And if you started to use it, you realized you had to change your tool set to build towards a Musel tool set, Musel compilation target. So it still didn't relieve you of the need to understand the OS layers under your application, even though you're using the container. I'm going to talk about an app with some different layers of abstraction. This is a machine learning app. And there's a diagram here. This user interface here is a Cosmonic application. Cosmonic provides a hosted wasmCloud platform as a service. The wasmCloud platform is 100% open core, open source. Cosmonic is built on top of wasmCloud because we want to make sure that we really push on the open source components and make sure that they're robust and solid enough to build a commercial service on. So I'm not here as a shill for Cosmonic. Everything I do today, you can do with open source wasmCloud stack. The reason I'm using this for a demo, because it has a nice user interface with lines and arrows. So we look at the some of the components of this picture. There's some purple boxes around here. These purple boxes contain the business logic of our application. And there are two blue boxes that contain services. One of them is an HTTP server endpoint. It receives the HTTP request with the image, passes it to the image UI. The image UI passes it to an inference API. Now, the inference API acts like a router. It's going to decide based on the inputs and various priorities and policies where it's going to send. Ultimately, the most important piece of this is the dark line that goes to the backend inference engine. The inference engine does a recognition of the picture to identify what's in the photo, and it sends it back with a ranked list of categories. Let's go take a look at this right now. So I'm going to choose an image here. Let's say I pick coffee cup. So we've sent the image to that inference engine through the inference API component, and it's come back with an estimate that with 84% confidence, that's a cup of espresso. And has some drips, so maybe it's chocolate or a candle. Now, going back to this picture, talk about some more of these images. The inference engine is not specific to image processing. It can handle other kinds of machine learning models. For image processing, we need to do a pre-processing step. The picture needs to be normalized into a 224 by 224 scale, and we also normalize the color space. And so after the inference API receives the image, it first sends it to a preprocessor, which rescales it and creates a tensor. A tensor is an array of floating point numbers, usually, sometimes integers. It's a multi-dimensional array. It's passed to the inference engine, and then the inference engine takes the results, which are a ranked list of categories, sends them to the post-processor. So the post-processor turns the results into something that's informative for a human. In this case, the text display that tells us what are the rankings and what are the guesses. Now let's look at the code behind this. So this is code from that inference API engine component in purple. First thing it does, it receives this put from the web server, and inside that put request, there's a body of the image, and it's going to send it to this pre-processing stage, to this actor. The actor is this kind of purple component, and it uses a familiar name, just a string name, to send that message. This is the entirety of code that it takes to send a message to an actor. There's no TCP stack, there's no serialization, there's no DNS lookup. There's just, hey, I want to send a message. Who are you going to send it to? And what's the data you're going to send to it? The next two lines here are a routing function. It's going to, based on the input data and the priorities of the application, it's going to choose a model and link. I'm going to talk about the model and link in a little bit. and then it's going to send it to the prediction engine, where it's going to create that ranked list. Prediction engine returns just a bunch of numbers, so we need the post processor to turn that into text for us. And again, this is the entirety of code that this component needs to send a message from one actor to another actor. And then we reformat the result in JSON. Now I did kind of gloss over this. What is this predict function? That's down here at the bottom. Here's the entire predict function. We take the data, put it into an inference input with the tensor data that came out of the preprocessing engine. And we create a connection with a link name. It's just a symbolic name for the kind of backend service we want to use. And we call predict function. That's all it takes. This is pretty high level. There's just business logic here. There's some math to manipulate arrays, but it's just business logic. There's no NFRs in here. What is this magic that allows us to accomplish this? Is it alien technology? Oh, sorry, you weren't supposed to see that. One of the underlying layers is WebAssembly. WebAssembly is an open standard for a compile target of an abstract machine. Some people compare it to the JVM, but it's lighter weight. It's also secure, provides a secure sandbox. When you're running untrusted code in your server, that untrusted code cannot access any system service like the file system or sockets, networking, or even a clock, unless it's given explicit permission. WebAssembly is also portable. It's running on every major browser, every major mobile device. Already has WebAssembly built in to the browser. You're already using WebAssembly today if you've used Google Earth, if you've edited a photo with an Adobe Web App in Photoshop or Lightroom. You're already using WebAssembly. It's because it speeds up the user interface. It's fast. It is close to native speed, and it has microsecond startup time. It's also polyglot. So the code we just looked at is Rust. We also have people using TinyGo, a variation of the Go language, to build WebAssembly components. And just this week, other projects are announcing Python and Java compiling down into WebAssembly targets. Unlike the JVM, where you need to use a Java-like language, WebAssembly really is polyglot. Now, of course, WebAssembly needs some orchestration. That's the job of wasmCloud. wasmCloud is an open source project. One of the key abstractions is capabilities. A capability defines an interface where your actor component can talk to another component, another service in the system. And that capability definition is independent of how it's implemented. So for example, I can write an app that needs a key value store, and using the key value capability, I can connect it to a Redis server on my laptop. Then when I'm deploying it to production, I can use DynamoDB, and my code does not have to change. Another important feature of capabilities is that they're signed with a secure encryption key. So we know who created it, and that helps us track the supply chain. But also that signature includes the capabilities that this component should be allowed to access. And there's no way in production that a component can access a service if it wasn't signed with a permission to do that. One of the phrases the wasmCloud developers use is sketch to scale. You think of an idea, I draw a sketch, and like you saw in the Cosmonic UI, fairly simple component to component interaction. And the code is not that different from that boxes and arrows diagram. And we don't have to spend a bunch of time figuring out the NFRs. It works whether that server is in any location and at any capacity, if it's behind a load balancer or it's redundant. I'm going to go up the stack another layer and talk about the machine learning inference capability. The inference capability provider was created by Christoph Brewing of BMW. And it allows us to abstract the engine we're using, whether it's ONNX or TensorFlow, and the model, whether it's ResNet or MobileNet. In addition, there's a WASI-NN interface created by Andrew Brown and a team at Intel, which allows us to abstract the form of a tensor, this self-describing multidimensional array, which is independent of whether your machine is big endian or a little endian. And there's also a Bindle server that was created by the DACE Labs group at Microsoft, which provides an artifact repository with well-known URLs that we can use to distribute our machine learning models. And we can do updates in the field. It's pretty common when you're doing testing of machine learning, you might find that one model works better than another model. Maybe tree works in one case and a support vector machine works in another case, or a neural network works in another case. And if our app can be written in a way that's independent of those models, then we can swap them out at runtime. All of these components here are open source. wasmCloud and WASM has a large community of contributors. It's an ecosystem that's healthy and growing really well. So again, let's look at the stack of building a wasmCloud application. You've got your actors. That's where you put the business logic. Because they don't have the overhead of all the libraries, they tend to be pretty small. We do see WebAssembly modules on the size of 10K to 100K. That's 3 orders of magnitude smaller than a 100K Docker container with a typical Java app. The actors access the outside world with capability contracts, like key value or the inference engine that we just demoed. And the wasmCloud host is also able to route requests to capability providers. Those are created by the open source community, and you can also create them as part of your app. Again, when a wasmCloud actor is talking to a capability provider, it has no knowledge. It shouldn't care where it is. It's independent of the topology of the network and the location of the services. I don't have time to talk about all the underlying components at the bottom of this diagram, but one thing I'll talk about is NATs. When Kevin Hoffman, the CTO of Cosmonic, was creating wasmCloud, he wanted to have a messaging layer that abstracted away a lot of the complexities of messaging. NATS provides reliable, guaranteed delivery. It provides encryption of messages in transit. In combination with the wasmCloud host, NATS together are building the routing paths across the network, constantly monitoring the health of the system with health checks and pings, and they're able to route messages as efficiently as possible. Now I'll note that you can run this stack on a Raspberry Pi. You can run it on a Coral dev board. If your IT department says you need to put the app in a Kubernetes pod, you can do that too. We're compatible with that. It does have some overhead, but it works. Let's come back to the app. When we sent the picture to the MobileNet backend, it had an 84% confidence that it was looking at a cup of espresso. But what if we used a different model? What if we used ResNet 152? ResNet 152 is a 152 layer neural network. that is bigger. It's a couple hundred megabytes. You probably wouldn't put it on most mobile phones, but for a lot of pictures, it has higher accuracy. So we're going to choose the same cup of coffee, and ResNet gave it, boom, almost 100%. That's a cup of espresso. So, of course, in a real user app, we're not going to give the user a choice between models. That's going to be baked into our app, and our app will make a decision based on some other requirements like accuracy or latency. Another important requirement to consider is privacy. We keep things local to our device and not send them to the cloud, then we're revealing less personal information. What if that app was screening for melanoma, a cancer, skin cancer? Now, a lot of times when you send something to a machine learning tool, it might come back with a pretty high confidence. So maybe it says 90% confidence it's not cancer. After it's done the recognition on a local device that gives you maximum privacy, didn't send any data to the cloud. And you go, great, 90%, keep using sunscreen, have a good day. Or if it says 90% confidence that this is cancer, go see your doctor immediately. Or maybe it's in the gray area. Maybe it only has a 50% or 60% confidence. Then we could present the user with a choice and say, if you're willing to reduce your privacy requirements a little bit, we can send this to the cloud, where we can get a better recognition and give you something with 80 or 90% confidence. Then we're giving the user a choice about things they care about. Of course, they don't care about ResNet or MobileNet, but they care about privacy and accuracy. And so instead of giving our app this user interface where you choose the model, maybe we give them choices on things like privacy, and that's where we do the first pass. Now, how many apps give you that choice? Usually, you just get what you get. But because we're building our app with higher levels of abstraction, and because we're not having to spend as much time editing YAML files and debugging DNS, we have more time to build these abstractions. And because we're not having to worry about keeping track of the network health and know where every server is, we've got the ability to give the users more control over their own data. This opens up a whole bunch of opportunities for building businesses for apps and for machine learning. Imagine that we've got a bunch of servers denoted by the rows on the left. We've got ability to process a machine learning workload on a local device, your mobile device, or something on the LAN. Maybe it's a game server with a GPU, or a cloud server, or a cloud server with a bank of GPUs. And meanwhile, the system, wasmCloud host, is understanding the network topology and collecting data about what's available, and is assessing the speed and the connectivity of the network. And then we can put into our app policy decisions that, based on privacy considerations or accuracy considerations, and again, give those choices to the end user. Making those decisions is as simple as looking up a string name in a matrix. We can also enable different kinds of business models. We could have a dictation app with speech recognition that offers higher performance for bulk users, or higher capacity, or lower latency for certain applications. And it's only possible to have these kind of business models if the software can support that kind of flexibility. And we have that kind of flexibility if we have the right levels of abstraction. So in summary, what we want to do is build apps without the gobbledygook. With capability providers like the ML inference engine and other capability providers, we can abstract over location. We can abstract over which model we're using, what engine we're using, where things are running. And we can make it easier for devs to move from pilot to production without changing code, untangling the dev from apps. That brings joy to developers. As it happens, that's the mission of Cosmonic, to bring joy to development. With these tools, we can deliver features and values that delight our customers. If you want to learn more about wasmCloud, go to wasmcloud.dev. You can sign up for the community Slack, and it's all open source on GitHub. If you want to learn more about Cosmonic, you can go to cosmonic.com, sign up to join our free developer beta. And I look forward to seeing the new generation of apps that you build on these platforms.